What's up, guys? Welcome to Venom Pronov Academy. Today we're starting the discussion in foundation mathematics, and we are simply going to start with the first topic, which is set theory. And foundation mathematics is simply one of the courses taken by the guys doing natural sciences and those doing A levels. Now, I know some of you might be wondering why we are starting the discussion of mathematics by looking at sets, because sets is one of the things that we did back in high school, and it was super boring for some of us. But then, just like the way they taught us in biology to say cells are the basic building blocks of all living organisms, the same applies to mathematics. Without the sets, without the knowledge about sets, without the interpretation of sets, you're going to find the study of mathematics to be a little bit tedious for you. So now, this is not the only thing that we are going to look at. We are going to look at a lot of things: the types of sets, the set representations and notations, the set symbols, the set laws, and other things under the discussion or under the topic set theory. But in our today's video, we're simply going to focus on set symbols and notations. So yeah, what is a set? A set is any collection, class, or list of objects, and these objects are simply going to be referred to as elements or members of a particular set. All right. So now, it's very important and very imperative for you to understand the differences between sets and elements. Elements are contained inside the set. A set is what is containing elements. So there are certain differences that exist in the way you are going to denote these two things. Firstly, when you are representing a set, it's always going to be represented or denoted by an uppercase or a capital letter. Let's say A. This A represents a set. But when you are representing or denoting an element, it's going to be represented by a lowercase or a small letter. So we can say set A contains the element A, B, C. But we cannot say set A contains the element A, B, C. This is totally unacceptable. So now, we know of a lot of things under sets, and we know of what a set is. We know how you are supposed to represent sets. Just the thing that I'm talking about. Now let's quickly kick into set symbols and notations, because that's the most important thing that we want to start discussing. So set symbols and notations. These set symbols and notations are very important because in the study of mathematics or under the set theory, we are simply going to have less of the words and more of the symbols and the notations that are going to be used. Hence, we are expected to understand and correctly interpret this for us to understand what a particular statement is trying to communicate. Okay? So, basically, one of the first things that I want you to remember is the aspect of a subset and an empty set. We know that a subset is simply a set within a set. And we know that an empty set is a set possessing or containing no elements or members. Now, having looked at subsets, or having talked or been reminded about subsets, I want us to now talk about set inclusion, because the aspect of subset simply reminds us of set inclusion. So when we are looking at set inclusion, we are basically talking about two major things, and these things are basically confused. People fail to distinguish which one is which and what this is trying to represent. So I want us to know that under set inclusion, we basically have two symbols, which is this and this respectively. Okay, I repeat, these symbols denote set inclusion. Okay, set inclusion, and not element or member inclusion, but set inclusion. So we've got this and this, which is simply trying to communicate something to us. But what are these symbols trying to mean? Let me give you an example. Let's say we've got set A, and set A contains the elements 1, 2, and 3. And we've got set B, and set B contains the element 1, 2, 3, and 4. Okay? So now, I want us to understand when we use this symbol and when we use this symbol. I know most of you remember the aspect of a subset or the aspect of a proper set rather, and an improper set. So I want to make a statement here. Know that, or remember that, a set is always a subset of itself. And also note that an empty set is a subset of each and every set. Okay? But remember that a set is never a proper set of itself. So now I want to explain on the aspect of proper set and improper set so that we properly distinguish what this means. And we are properly going to understand the entire science, or how it comes back to that, because, okay, this is foundation sciences, right? So we are going to understand the science or the motive behind these symbols when we start dealing with power sets, we are properly going to interpret or why we come to this conclusion. We are simply going to comprehend that when we look at power sets. So in the meantime, I want us to focus on these two sets. We know that set A contains 1, 2, and 3, and set B contains 1, 2, 3, and 4. So in this statement, I can say that all the elements in set A are also there in set B. But there exists at least one element in B which is not there in A. Thus, I can say A is a proper set or is a proper subset of B. And I'm using this symbol. What is this symbol trying to tell me? It's trying to tell me that all the elements in B, all the elements in A rather, are there in B, but at least one element which is in B is not in A. So it's a proper subset. Okay? We can see that 4 is not there in set A. But if I was to give another example where I get set A to have 1, 2, and 3, and set B to have 3, 2, and 1, then I can make a statement to say A is a subset equal to B. Okay? Why? Because all the elements in A are also there in B, and there exists no element that is in set B which is not in set A. Thus, I'm going to use this symbol. I hope you guys can properly differentiate between these two symbols. If I use this, it's same applies. Let me try to draw it like this. Let me say I've got set A and set B here. You see that all the elements in set B or in set A are there in set B, but at least we could have numbers here. Let me say 1, 3, and 4, but here I put 2 and 5. I know that all the elements in set A are also there in set B, but 2 and 5 is in set B but not in set A. So I'm going to use this symbol. Provided there is one element which is there in one set and not the other set, then we are going to call that a proper subset. But if all the elements in both sets are there and there exists no element which is in one set and not in another set, then we are simply going to use this notation. Okay? Others, when representing this, are going to use these two symbols. So just bear in mind, this one is simply equal to this one. Okay? That's what it simply means. And in this case, when I'm dealing with proper set, I can make a notation and say A is not equal to B. Why do I say so? Because I know that in B there is an element which is not there in A. But when I'm looking at improper sets, I can tell, or I can put a notation to say A is equal to B. Why? Because all the elements in B are there in A. Okay, so this is the aspect of set inclusion. In another dimension, I want you guys to know that there's what we call supersets. So supersets are simply the opposite of these things that we are looking at. I want to say all the elements in B, all the elements in A rather, are there in B, but not all the elements in B are there in A. Or I want to say B is containing A. In other words, it's same as, okay, let me make it more practical. If I say 1 is less than 5, okay, or let me say A is less than B, is it wrong if I say 5 is greater than 1, or if I say B is greater than A? No, it's basically the same thing. So this is the aspect of power sets, or supersets rather. So when we talk of supersets, what we are simply trying to do is we are trying to reverse the notation and put it the other way around. We don't want to say A is contained in B, but we want to say B is containing A. So when you see those notation, instead of saying A is a subset equal to B, I can say B is a subset equal to A. Or instead of saying A is a proper subset of B, I can say B is a superset of A. So here I can, you just flip the symbol, you make it face the other side. So it's simply the same thing, just like the way we've extrapolated it here. So now I want us to talk or to look at element inclusion. So under element inclusion, we know that we basically have two symbols, right? Element inclusion, the one we are looking at was set inclusion. Now this is element inclusion, and you guys know that we only have two symbols. We've got this one and this one respectively. So this one means a member or a particular element is a member of a particular set, or it is not a member of a particular set respectively. So this one means it's a member of, this one it means it's not a member of, or it's not among the elements belonging to that particular set. So let me say set A contains 1, 2, 3, and set B contains 1, 2, 3. So I can say 1 is a member of A. Why? Because 1 is in A. And I can say 4 is not a member of what? Is not a member of A. Why? Because you can't see 4 amongst the elements that are listed there. But this comes in to remind us about something. If you know that all the elements of a particular set can be counted, we call that a finite set. I know the pronunciation of that word might be different from others, but yeah, it's a finite set, meaning all the elements of that particular set can be counted. And I can say A, or the number of elements in A, is simply equal to what? To 3, because I can count them, right? The number of elements in set B is simply equal to what? To also 3, because there are simply 3 elements in there. But then there's an aspect of what we call cardinality. Okay, now people are simply going to tell you, or different books are simply going to tell you to say the cardinality of a set is simply the number of elements in that particular set. Sometimes it does not hold true to define it like that. So I would love you to understand it in such a way that you know what I mean as I'm going to give this definition. The cardinality of a set is the number of non-repeating elements of a particular set. Let's say we've got set A, and set A has got 1, 2, 2, 3, 3, 4, 4. Okay, then they ask you to say what is the cardinality of this set. Let's use the first definition that I gave. The cardinality of a set is the number of elements in that particular set. So based on that definition, how many elements do we have? 1, 2, 3, 4, 5, 6, 7. Then our cardinality is simply equal to 7. But if we revise it and say the cardinality of a set is the number of non-repeating elements of a particular set, then we are simply going to regard whether we've got 5 2s or 7 what, we are simply going to count it as 1. If an element is existing more than one time, then we are simply going to regard it as 1. We are simply going to count it on 1. Thus our cardinality is going to be 1, 2, 3, and 4. So the cardinality of this set is simply going to be 4. So this is what I wanted us to look at, the set symbols and the set notations. Other symbols means this, it's equal to. This one means it's not equal to. And I want you guys to know that we've got this one, which means it's equivalent. It's simply trying to show us the equivalence. It does not mean it's equal to. A set can be equivalent to another set, but not equal to another set. For example, if I say this is 1, 2, 3, and I say set B is A, B, C, I can say set A is equivalent to B. Okay, but set A is not equal to B. Why? Because they've got the same number of elements, thus they're equivalent, but not the same elements, so they are not equal. So set equivalence does not necessarily mean they are equal, but in the other dimension, if you look at the equality of a set, it's simply going to match the equivalence. If two sets are equal, then they're also equivalent. For example, if I put set B to be 1, 2, 3, then I'm going to say set A is equal to what? It's equal to B, because they possess the same element. If they are equal, then they're also what? Equivalent. Thank you very much for watching, and please share and like and subscribe. Don't forget to subscribe, and if you find this video beneficial, then please share it to your friends, and please give us the comments so we know what to work on, so we can provide our best services at hand. It's Prunov.